Now, I want to take a moment to point out that subnetting makes sense from the binary perspective. In other words, when we take the IP address and the subnet mask and convert them to binary, I have the IP address on this row here, I have the subnet mask on this row converted to binary, that the computer and the router are able to logically AND or combine the IP address and the subnet mask and find the network address. In other words, this ANDing process is a logical process of ANDing. So a true and a true makes a true, 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 false and a true makes a false. And if we do that and logically AND the IP address with the subnet mask, we get the network address. So 192.168.1.10 logically ANDed with 255.255.255.0 produces the 192.168.1.0 network. This is at the core of the IPv4 address and subnet mask and subnetting in general. What about non-classful subnet masks? We've seen that the Class C subnet mask is /24. We've seen the Class B subnet mask /16 and the Class A subnet mask /8. But what if we use classless masks? In other words, what if we have a /25 subnet mask or a /18 subnet mask, creating a 255.255.192.0 subnet mask? Or for that matter, a /12 subnet mask, 255.240.0.0. How does that work, and how does that change the networks that are created by the combination of the IP address and the subnet mask? This is called subnetting. I'll explain it using an example scenario. Let's start with a classic Class C network like 192.168.1.0 with a /24 or 255.255.255.0 subnet mask. If we want to subnet this 192.168.1.0 network, what we need to do is go into the subnet mask in binary, which we can see on this row right here. And what we do is, to change the subnet mask, we borrow bits from the host portion of the address. This is done from left to right. So I could take this first 0 here on the left and change it to a 1. And now I've effectively changed the subnet mask from /24 to /25. In other words, if I convert this back to decimal, it's now 255.255.255.128. This completely changes the nature of the network. We now have a /25 subnet mask, and we only have 7 host bits. So starting from a /24, we now have borrowed 1 bit from the host portion. We call this 1 bit a subnet bit. If we look at it from the perspective that we started with /24, we've added 1 bit. So we could say that subnet bits, we now have 1 bit, or 2 to the first power, creating 2 subnetworks. Host bits, we have 7 zeros now. So host bits are 2 to the 7th power, or 128, minus 2 for the network address and the broadcast address, leaving us with a total number of possible hosts on the subnets of 126. So by borrowing 1 bit from the host portion of the address, we create 2 subnetworks, each subnetwork with 126 hosts. The subnetworks are the 192.168.1.0/25 subnetwork and the 192.168.1.128 subnetwork /25. We can prove that this is the case using logical ANDing to prove how the router or a computer would take an IP address with this particular /25 subnet mask and derive the resulting network address. In other words, let's put in a host address. I'll put in the host address here, and I'll say let's put in the address 68. So I changed this to a 68. So now we've got host 192.168.1.68. So this needs to be a 1. That's the 64. And then we need to add the 4-bit here. So now we have 68. If we logically AND the IP address here with our new subnet mask /25 here, let's see the result. We'll get a 1, a 1, a 0, 0, 0, 0, 0. So that's 192. And then here, the result is 101, 01, 168. And then all zeros here and a 1. This is a 1. And now if we look at this last octet, a false and a true makes a false. A true and a false makes a false. And then we get all zeros here. So the address, the network address, is the 192.168.1.0 network. So host number 68 is on the 0 network. Well, this makes sense because if the next subnet is 128, if we put in a host address larger than 128, we'll see if it falls in this subnetwork. So let's change it slightly. I'll change the host address to 138. So now I'll change this, put that as 0. So there's a 128 bit. I'll make this a 1. And I'll put a 1 here. So 128 plus 8 plus 2 is 138. If we do the ANDing again, we see that a true and a true makes a true. And then we have falses all the way. And now the resulting network address is 128. So when we take the IP address with the /25 subnet mask, we see that the network address is 192.168.1.128. So we've created two subnetworks from the single 192.168.1.0/24 network. We've created two subnetworks. The subnetworks go from 1.0 all the way up to 1.127, with 0 being the network address and 127 being the broadcast address. And the second subnetwork starts at 128, so this is the network address because it's the first address, all the way up to 255, and since this is the last address, this is the broadcast address. In other words, the first address in the subnet is the network address, and the last address in the subnetwork is the broadcast address. This process is called subnetting. This video focuses on subnetting and how to find your subnetworks easily and quickly using the magic number trick. Let's say we're subnetting a 192.168.1.0 network /24. I have the IP address and subnet mask in decimal here, and I have them listed in binary here. The network portion of the subnet mask and the host portion of the subnet mask. To subnet this network, what I can do is I can borrow 1 bit from the host portion of the subnet mask, and now I have 1 subnet bit. This changes the subnet mask from /24 to /25. If I borrow 1 bit from the host portion, I have 1 bit, or 2 to the first power, makes 2 possible subnetworks. The subnetworks I've created are the 192.168.1.0 subnet and the 192.168.1.128 subnet, both /25. The hosts on each network are 126 usable hosts. We have 7 zeros here, and 2 to the 7th power is 128, minus 2 makes 126 usable hosts per subnet. If I decide to borrow 2 subnetwork bits from the host portion of the original 192.168.1.0/24 network, I now have /26. I've borrowed 2 bits, so now I have 2 to the second power of subnet bits, so I have effectively 4 subnetworks. The 4 subnetworks are listed here. For host bits, I have 6 zeros in the host portion of the address, and 2 to the 6th power is 64. Minus 2 for each subnet makes 62 usable hosts per subnet. The subnetworks that are created are the 192.168.1.0 subnet, the 64 subnet, the 128 subnet, and the 192 subnet. Notice how the number of borrowed bits and the number of host bits determines a lot about the subnet. If I borrow 3 subnetwork bits, I now have a /27, so it goes from /24 to /27. I have 3 subnet bits. 2 to the 3rd power is 8. 2 times 2 times 2 is 8. And you can see that I now have 8 subnets or 8 subnetworks created from the original 192.168.1.0 network. Each subnet is now /27. Notice that there are now 32 hosts or 30 usable hosts per subnetwork. We could go up to /28, and now I have 4 subnetwork bits. Notice that the subnet mask has changed from 255.255.255.0 when it was /24 to now 240. I now have 16 subnetworks, or 2 to the 4th power, and there's 2 to the 4th power of hosts per network, so there's 16 or 14 usable host addresses per subnet. Borrowing 5 bits looks like this, and borrowing 6 bits looks like this. I've now borrowed 6 bits from the original 8-bit host portion of the original /24 network, and I now have 2 to the 6th power of possible subnetworks, meaning I have 64 subnets. The host portion of the address is now only 2 bits, or 2 to the 2nd power, meaning there's only 4 host addresses per subnet. Now, if you have 4 host addresses, you have to leave room for the network address and the broadcast address, so 4 minus 2 leaves only 2 usable hosts per subnet. Typically on a LAN, we do not go higher than a /30 subnet mask. Otherwise, you'll not have enough room for usable host addresses. In other words, we can't borrow any more bits from the host portion, or we won't have enough addresses for hosts. You might be asking yourself how I was able to discern the different subnetworks from the subnet mask or subnet bits that were borrowed. There are many different ways to derive the subnetworks from the subnet mask, but my favorite is the magic number technique. The magic number is simply the place value of the last one in the subnet mask. So in this situation, we have a /25 subnet mask. We have 25 ones, and the last one is the one here all the way on the right, highlighted in red. This one, if we look at it according to this octet, is in the 128th place. If we think about the place values of 8 bits, this is the 128th place. So the magic number in this situation is 128. The magic number tells us where to find the networks. It tells us that the networks will go up by 128. So in this case, the first network, which is always 0, so 192.168.1.0/25, and from there the networks go up by 128, so the next network is 192.168.1.128. Let's see how this works borrowing 2 bits from the host portion. Now I have borrowed 2 bits from the host portion of the subnet mask. The magic number is now the last binary one, which in this case is in the 64's place. So the magic number is 64. The magic number tells us how to find our networks and lets us know that the networks will be going up in increments of 64. So for instance, the first subnet is always 0, so 192.168.1.0/26. The next subnet is 64. 64 plus 64 is 128, and 128 plus 64 is 192. You can see how the subnets are going up by 64. There's only 4 subnets because we've borrowed 2 subnet bits. Also, we can go no higher than 192 because 64 plus 192 is 256, and that's too large a number. Let's see how it works with 3 bits. With 3 bits, we now have a /25, 26, 27 subnet mask, /27 subnet mask, in decimal 255, 255, 255, 224. The last one in the subnet mask is our magic number. In this case, it's in the 32's place in the binary conversion table. So the magic number is 32. If we look at the networks, we'll see that they go up by 32. The first network being 0, 192.168.1.0/27, then the 32 subnet /27, 64, 96, 128, 160, 192, and 224. The subnets go up in increments of 32, following the magic number. Now that we see the pattern and how the last borrowed bit affects the location of the subnetworks, let's try it with a /28 subnet mask. Now I have the 192.168.1.0/24 network. I want to subnet it, changing it to /28. /28 means I borrow 4 bits in the subnet mask, so I now have 28 ones counted from left to right. 255, 255, 255, 240 subnet mask. 128 plus 64 plus 32 plus 16 is 240. The last one is in the 16's place. This is the 128's place, the 64's place, the 32's place, the 16's place. So the magic number is 16. We'll see that the networks go up by 16. The first network is always 0, so 192.168.1.0/28. I'll copy this and paste it, and the next network will be the 16 network. Why? Because the magic number is 16, because the last one is in the place value of 16. The next network will be 32. And the following network will be 48. And after 48, 64, and so on and so forth. The networks will go up by 16. In each network, we have the host bits, 4 bits for hosts, which is also 2 to the 4th power of 16. So the network will go from 0 up to 15, with 0 being the sub-network address or network address, and 15 being the broadcast address, and the next subnet is the 16 subnetwork. Now let's try creating /29 subnets. We can see that that involves borrowing 5 bits from the host portion of the subnet mask, and that the last one is in the 8th place. So the magic number is 8. The networks will go up in increments of 8. So starting from 0, we'll have the 8 network and the 16 network and the 24 network, and so on and so forth, all subnets being /29. For the /30, we see that the last one is in the 4's place, and that the networks will go up by 4. So similarly, the networks will go up in increments of 4. So the first network is the 0 network, then the 4 subnetwork, then the 8 subnetwork. Each subnetwork will have 4 host addresses, in this case 0 to 3, 0 will be the network address, 3 the broadcast address, and the addresses between 1 and 2 will be the usable host addresses. Only 2 usable host addresses in a /30 subnetted network. You might ask yourself, will this technique, the magic number technique of looking at the place value of the last one in the subnet mask, work in other subnetted octets? In other words, if we're starting from a class B /16 network address or a /8 class A network address, would this technique work? And it does. For instance, if we take a 172.16.0.0 network /16, you can see in this scenario, I've subnetted it to a /23 subnet mask. In other words, I've taken the original 16 network bits and borrowed 1, 2, 3, 4, 5, 6, 7 ones from the host portion of the subnet mask. In this situation, the last borrowed one is in the 2's place. So the magic number in this situation is 2. This means that the subnets will go up by 2 in this octet here. So in other words, our first subnet will be 172.16.0.0/23, and the next network will be 172.16.2.0/23. The only difference is now, instead of 16 host bits like we would have had in a /16 network, we now have 9 host bits. So 2 to the 9th power, meaning we have 512 minus 2 would be 510 host addresses that we can assign. In other words, the network goes from 0.0 all the way up to 172.16.1.255. So the first usable host address would be 0.1, and the last usable host address would be 1.254. The next subnet starts at 2.0. After that, the networks continue to go up by 2. In other words, the next subnet will be the 4 subnet, and then the 6 subnet, and the 8 subnet. Notice that the networks are going up by 2, but in the 3rd octet, not in the 4th octet. The only difference not to be confused on is the larger number of host addresses that you'll experience when you subnet in this octet or in the 2nd octet. You can see how the magic number technique can help you quickly locate the networks or subnets. You are a network administrator and you're tasked with creating 2 equal-sized subnets from the network address 192.168.1.0/24. The first thing we'll do is write out the subnet mask in binary. You can see we have 24 ones going from left to right. What we'll want to do to subnet this network is borrow bits from the host portion of the subnet mask here. You can see that I've put up a table with the 8-bit place values of the 8 bits in the last octet. If we borrow 1 bit from the host portion and change this 0 to a 1, we've now changed the subnet mask from /24 to /25. By borrowing 1 bit from the host portion, we have 2 to the first power, or 2 subnetworks that we create. The subnetworks will go up by the place value of this binary digit. We can see that the place value is 128, so the networks or subnetworks will go up by 128. In other words, the first network will be the 0 network /25, and the second subnet will be 128/25. We've now created 2 subnetworks from the original 192.168.1.0/24 network. We can use these subnets now for the 2 networks coming off of router R1 here. In this situation, we're tasked to create 4 equal-sized subnets starting from the network address 192.168.1.0/24. If you look at the diagram, the network administrator actually only needs to create 3 subnetworks. However, this will not be possible because subnets are created in powers of 2. So we have the options of creating 2 subnets, 4 subnets, 8 subnets, and so on, going up in powers of 2. I'll show you what I mean. First, I'll write out the subnet mask in binary. So we'll be borrowing bits here from the host portion. If we borrow 2 bits from the host portion of the subnet mask, we now have 2 subnetwork bits, and 2 to the second power is 4, so that will create 4 subnets. The last one in our subnet mask is in the 64's place, so the subnets will go up by 64. In other words, the first subnetwork will be 0/26, since we've added 2 subnet bits and we now have 26 ones. The next subnetwork will be 192.168.1.64/26, and then 192.168.1.128/26. Notice that they're going up by 64. And the last one, 192.168 192.192/26. We now have 4 equal-sized subnets, and we can use any of these subnets to accommodate these 3 networks in the diagram. In this situation, we need to create 8 equal-sized subnets starting from the 192.168.1.0/24 network. We actually only need to create 5 subnets, but since subnets are created in powers of 2 starting from 2, we'll need to create 8 equal-sized subnets in order to accommodate the 5 subnets necessary in this diagram. So first, I write out the subnet mask in binary, 24 ones for a /24 network. We're going to borrow bits from the host portion of the subnet mask. If we borrow 3 bits, we've borrowed 2 to the 3rd power of bits, and 2 times 2 times 2 is 8, so this will create 8 subnets. The last one in our new /27 subnet mask is in the 32's place if we look at it according to an 8-bit binary conversion table. So the last bit is in the 32's place. This lets us know that the subnets will go up in increments of 32. So the first network will be the 0 subnet /27, and the next subnet will be the 32 subnet /27, and then going up in increments of 32. 32 plus 32 is 64, and then the 96 subnet. After 96, we'll have the 192.168.1.128/27 subnet, and then the 160 subnet, the 192 subnet, and the 224 subnet. So as you can see, we have 8 subnetworks going up in increments of 32, the 0, the 32, 64, 96, 128, 160, 192, and 224. We can use any of these 8 subnets to accommodate the 5 subnets that we'll need to address all of these networks. An enterprise network requires 100 equal-sized subnets starting from 172.16.0.0/16. To subnet this network correctly, the first thing that I do is write out the subnet mask. There's my /16 subnet mask. I'm going to need to borrow bits from the host portion. If I borrow 1 bit, I have 2 subnets. 2 bits would be 4 subnets, 8 subnets, 16, 32, 64, 128. I'll need to create 128 subnets to meet the requirement of having 100 equal-sized subnets. So I've highlighted the borrowed bits in the subnet mask. We've borrowed 7 bits. 2 to the 7th power is 128, creating 128 subnets. The last one in the subnet mask is in the 2's place. So I know that the networks will go up by 2. So I can go down here and fill in the networks. The first network will be 172.16.0.0/23, because we have 23 ones now in the subnet mask. And the next network will be 172.16.2.0/23. And we can see that if I list out the networks will continue to go up by 2. And if we go all the way up, I'll skip a few here, the last subnet will be 172.16.254.0/23. If I was to list out all of the subnets, I would have 128 subnets. For hosts in each subnet, we have 9 zeros in our subnet mask, and 2 to the 9th power is 512, so we'll have 512 minus 2, so 510 usable hosts per subnet. An easy way to figure out the hosts is 8 zeros is 256 hosts, and every 0 added on doubles the number of hosts, so 256 plus 1 more 0 would be 512 hosts, minus 2 for 510 usable. In classless subnetting, we've seen how we can borrow bits from the host portion of the subnet mask, and that the last one that's borrowed is the magic number, meaning that the last one, if we look at the place value of the 8-bit grouping, the last one in this case is in the 32's place, so the networks go up by 32. Starting with the 0 network, we have the 32 network, then the 64, 96, 128, so on and so forth, but the networks go up by 32. What about when we're subnetting from a Class A or Class B network address and subnetting generally in the other octets? Let's take a look at another example. This time we have a 10.0.0.0 network address and a classful Class A subnet mask, and we're going to subnet it. So we've taken the 8 bits and borrowed 3 bits, and now we have a /11 subnet mask. The last one in the subnet mask is still in the 32's place. If we look at this 8-bit grouping in this octet right here, the last one is still in the 32's place. So the networks will go up by 32. So the networks are the 10.0, 32, 64, 96, and they're going up by 32, but in the second octet. The only difference is now we have a lot more host addresses. We have 8, 16, 21 zeros for hosts, which means there's over 2 million hosts per subnet. For instance, if we take a look at this 10.192.0.0 subnet, the next subnet is 10.224. So that means that the host addresses go from 0.1 all the way up to 10.223.255.254 as the last usable host, and 255 is the broadcast. The next address is 10.224.0.0, which is the next subnet. All of these subnets are now /11. What about a more difficult scenario? In this scenario, we need to create over 300 equal-sized subnets of 20,000 hosts each, starting from the 10.0.0/8 network. So we need to create a lot more subnets, and we need a lot of hosts. Looking at this situation, we know that we're going to need to borrow bits from the host portion of our subnet mask. The question is, how many bits will we borrow? If we borrow 1 bit, we have 2 subnets. Now we have 4 subnets, 8 subnets, 16, 32, 64, 128, 256, 512. If we borrow 9 bits, we'll have 512 subnets that we create, and that will be sufficient to meet the demand for 300 equal-sized subnets. What about the requirement of 20,000 hosts each? We have 15 zeros left for hosts per subnet. 2 to the 15th power is 32,768 minus 2 would be 32,766 hosts per subnet. That meets the requirement of having at least 20,000 hosts in each subnet. So this scenario would work. You can see here that I've now highlighted the borrowed bits from the subnet mask. I've also converted it to decimal here, 255.255.128.0. And I've already ascertained that the last one in the subnet mask is in the 128's place, so the magic number is 128. The subnets will still go up by 128, but they'll also need to go up for every number possible in the second octet. If we look below here, we can see our subnets. The first subnet will be the 10.0.0.0/17 subnet, then the 0.128 subnet, then the 1.0 subnet, then the 1.128 subnet. And as you can see, we're iterating through every possible number in the second octet and then going up by 128 in the third octet. If I was to list out every possible subnet, we'd go all the way up to 10.255.0.0, and the next subnet would be 10.255.128.0. /17 is our last subnet, for a total of 512 subnets. In a situation like this, there's many more subnets and many more hosts per subnet, but the rule of the magic number still applies. The basics of VLSM, or variable length subnet masks, works like this. 1. Subnets do not have to be equal sizes, as long as their address ranges do not overlap. So we can create unequal sized subnets. They do not all have to be the same size. 2. When creating subnets, it is easier to work from larger to smaller subnets. So for example, I have the 192.168.1.0/24 network. I subnet the network into 4 subnets /26 subnet masks. So the subnets go up by 64. I now have 4 equal-sized subnets. With VLSM, or variable length subnet masks, I can decide that I want to change one of these subnets and further subdivide them into smaller subnets, as long as the address spaces that I create, or the subnets that I create, do not intrude into the other subnets. For instance, I could take this 192.168.1.192 subnet. The address range for this subnet goes from 192 all the way up to 255. What I can do is I can say, instead of having this subnet /26, what if I take that address space and divide it into 2 smaller subnets size /27 each? If I do this, I effectively have created 5 subnets. The 3 subnets up here are 64 hosts each, and the 2 new subnets that I created from the 4th subnet are 32 hosts each. The reason I can do this is because my 2 smaller subnets do not intrude into the larger subnets. This is variable length subnet masks. In this situation, it has also allowed me to create 5 subnets, thus escaping the equal-sized subnet limitation of creating subnets in powers of 2. This gives me greater flexibility and allows me to create subnets of different sizes based on the requirements of my network. In this scenario, the task is to subnet the 172.16.0.0/23 network to create the following subnets: 1 network for 200 hosts, 1 network for 100 hosts, 1 network for 50 hosts, 1 network for 25 hosts, 1 network for 10 hosts, and 4 point-to-point networks for 2 hosts each. Before I begin to create these subnets, I need to check to see if I even have enough addresses in this address space to create all of these subnets. So by writing out the network and the subnet mask in binary, we see that we have a /23 subnet mask. Here's 23 ones in binary. The last bit is in the 2's place. If we look at this 8-bit grouping in the 3rd octet, we see that the last one is in the 2's place. That means the subnets would go up by 2. So the next subnet will be 172.16.2.0/23. So the address space that we're working with goes from 172.16.0.0 all the way up to 1.255. Let's see if this is enough addresses to create all of these subnets for this specified amount of hosts. I can see that starting from a /23 subnet mask, we have 9 host bits, so effectively there's 512 hosts. If we look at each one of these subnets that we're going to need to create, I cannot create a 200 host subnet, but I can create a subnet for 256 hosts. That number does not reflect the usable hosts, but the total number of addresses in the subnet. Similarly, I'm unable to create exactly a 100 host subnet, but I can create a 128 host subnet, a 64 subnet, a 32 subnet, a 16 subnet, and 4 host subnets will satisfy these requirements. If I add up all of these numbers, 256, 128, 64, 32, 16, and 4 subnets of 4, the total number is 512. So I'll have exactly enough host addresses to create these sized subnets and meet the requirements. Once again, these numbers here for the subnet sizes that we'll create do not reflect the usable host addresses, but the total number of addresses in the host portion of the subnet ranges, including the network address and the broadcast address. So let's get started subnetting this network using VLSM, variable length subnet masks, and working from largest subnets to smallest subnets in order to create all of the subnets required. So working from largest to smallest, the first thing I need to do is to create a network for 256 hosts to satisfy the 200 host requirement. What I can do is I can subdivide this single network of 512 hosts into 2 smaller subnets of 256 hosts each. So instead of having a 172.16.0.0 network /23, I change the subnet mask to /24. This creates 2 networks, 0.0 and 1.0, each subnet having 256 or 8 host bits. Notice how the subnet mask has changed from /23 to /24, and I now have 2 256 host subnets. What I can now do is keep the first of these subnets and subdivide the second one. To do this, I simply take this 172.16.1.0/24 subnet and change it from /24 to /25. So now I have the 172.16.1.0/25 subnet. This creates another subnet, 172.16.1.128. Both subnets have a magic number of 128, meaning the networks go up by 128. So I've taken this one network of 256 hosts and subdivided it into 2 networks of 128 hosts each. Now I have a subnet to meet this second requirement. Moving on from there, I'll keep the first of these subnets and then further subdivide the second one. So now we no longer have the 1.0 network in its place. We have the 1.0 subnet and the 1.128 subnet. Then I subdivide the 128 subnet into 2 smaller subnets /26 each. So now there's no longer a 128 subnet, there's 2 subnets in its place, a 128 subnet and a 192 subnet. Both of these subnets have a /26 subnet mask. If I was to write this subnet mask in the binary conversion table here, we would see that in the 4th octet, /26 means that the last one in the subnet mask is in the 64's place, and the networks go up by 64. Furthermore, with the /26 subnet mask, you only have 1, 2, 3, 4, 5, 6 host bits, and 2 to the 6th power is 64, meaning there's 64 hosts, 62 usable per subnet. I now have my 256 host subnet, I have my 128 host subnet, and my 64 host subnet. I can subdivide the second of these two subnets into two smaller subnets of 32 hosts each. To do this, I take the 192 subnet and subdivide it by changing the subnet mask from /26 to /27, creating two subnets of 32 hosts each. So now I'm no longer using the 192 subnet /26, I'm using it as a 192/27 subnet and a 224/27 subnet. From here, I still need a subnet for 10 hosts. I can take the second of these two subnets for 32 hosts and subdivide them to two 16-host subnets. To do this, we take the 224/27 subnet, change the subnet mask from /27 to /28, and now I have two smaller subnets. From here, I take the second of these two 16-host subnets. I only need one. The second one I'll use for 4 subnets of 4 hosts each. So now instead of the 240/28 subnet, I have the 240/30, the 244/30, the 248/30, and the 252/30 subnets. Looking at the subnets that have been left, we have the 172.16.0.0/24 subnet. This is good for 256 hosts. We have the 172.16.1.0/25 subnet. This is good for 128 hosts. The 172.16.1.128 subnet /26 is good for 64 hosts. And the 192/27 subnet is good for 32 hosts. The 224/28 is a 16-host subnet. And then the last 4 subnets /30 each, 240, 244, 248, and 252, are good for 4 hosts each. Once again, these sizes do not reflect the usable hosts in each subnet, but the total number of addresses in the host portion. For usable host addresses, you need to -2 from each subnet. If we examine the host addresses closely, we'll see that none of the subnets overlap. In other words, this 172.16.0 subnet goes from 0 all the way up, since it's /24, to 255. You can see that the next subnet starts at 172.16.1.0, so the two subnets do not overlap. Similarly, this second subnet goes from 0 to 127, and we can see that from host 0 to 127, the next subnet at 172.16.1.128/26, that there's no overlap. This subnet ends at 127, the next subnet begins at 128, and so on and so forth. In the end, we've created 9 subnets of different sizes: a 256, a 128, a 64, a 32, a 16, and 4 4-host subnets. This is VLSM, and it allows us to create subnets or networks specific to the needs of the network.